Hey everybody, it's Dr. J, and today we're talking about the wave equation. Let's talk about chemistry. All right, so today we're going to be talking about Schrodinger's equation. All right, so basically the key thing you guys want to understand about this is an equation that's going to help us basically figure out where our electron is, all right, as far as in our orbital. Okay, so now we can figure out the location of that electron based on this equation. Okay, so basically, right, we're able to do that because we understand that electrons can act as waves. Okay, and when they're acting as waves, we can use Schrodinger's wave equation. So in this case, little typo here, but it's going to be E wave function equals to our Hamiltonian, so our H wave function. Now, do you guys need to understand this? No, you don't need to understand none of this unless you're taking quantum. We're not about to go that deep. All you guys need to know is that this is the wave equation. This is energy equals the Hamiltonian. It represents the total energy. We're not going that deep. Quantum mechanics. Well, little quick story. That was one of the toughest classes I've ever taken in my life. That's just a side note. That's a quick story. That's it. It's just a hard class. Y'all don't need to know that. All right. So many energies can be found, each corresponding to an orbital. This is what we're focusing on, where those electrons are in those orbitals. Okay. And those orbitals correspond to a standing electron wave of a specific shape. So basically, we got to understand that because of this wave equation, we know where the locations of electrons are now. Now let's talk about what everybody loves. The answers, right? Let's talk about those answers. So we're going to talk about today the solutions to Schrodinger's wave equation. Basically, we call these answers quantum numbers, okay? So these are the quantized solutions to that wave equation. Now, these quantum numbers are going to help us with a couple different things. It's going to tell us the size, the shape, and the orientation of that orbital. So we got four quantum numbers we're going over today. We got our principal quantum number N, angular momentum quantum number L, magnetic quantum number ML, and then our spin quantum number MS. Okay, and what we're going to see here is that, this is just an example, but basically each quantum number will impact the next until we ultimately get to our orbital. You'll see this again at the end. But let's jump to our first quantum number, principal quantum number N. Okay, so basically, what you guys need to really understand about principal quantum number is that this is a quantum number that's going to tell you about your size and energy of an orbital. Okay, so basically, that larger that N is, right? N's one, two, three, four, right? The larger that N is, that means that you got more energy in that orbital. Okay, and if you got more energy in that orbital, that means that you're going to have a larger orbital. And if you got a large orbital, that means that you're going to have a lot of different electrons in that orbital. And if you got a lot of different electrons in that orbital, well, that means that, those electrons are not strongly bound to the nucleus at the end of the day. Okay, so basically, if your N gets larger, that means you got a lot of energy in that orbital. Okay. Now, one thing we will see about this is basically we look over here. This is Rydberg's constant for hydrogen. Okay, so basically, this is dealing with energy transitions. We're not going to get into that today. The key thing I want you guys to understand, and if you want me to get into that, just let me know. I could do a whole nother video about that. But this is the key thing about principal quantum number is that energy is negative because our electron's energy is lower by our interacting with the nucleus. Okay, so basically, if we increase our energy, we're going to see that as we increase our energy, our orbitals will become closer together. That's essentially it, everybody. So once we get to like N3, N4, we can see the gap between these have significantly gotten smaller compared to when we look at 1 and 2. So key thing about this quantum number, principal quantum number, is going to tell you the size and energy of your orbital. The next quantum number is angular momentum quantum number, or L. So basically, this number is telling me the shape of my orbital. Now, in order to find our L, okay, basically we're going to do our N, principal quantum number, minus 1. That's how we find our L. Simple as that. So if I got n of 3, right? If I do 3 minus 1, that's going to be 2. Now, let's talk about this real fast. Once you get that 2 for your value of L, you actually will have the numbers before that 2. So you're going to have 0, 1, and 2. Now, what exactly does these numbers mean, right? Well, those numbers mean a certain thing. So basically, if you have a value of 0 for your angular momentum quantum number, that means that you have a s orbital. If you have a value of 1, you have a p orbital. If you have a value of 2, you have a d orbital. If you got a value of 3, you have a f orbital. Now, all of these orbitals look a certain way, okay? In this case, s orbitals are going to be spheres. P orbitals look like 2 balloons tied at a knot. D orbitals look like 4 balloons tied at a knot. And then F orbitals look like 8 balloons tied at a knot. Okay. So they look very similar, but I will have a upcoming video just talking about the orbitals real fast. But essentially, guys, you want to know this. 0 equals S, 1 equals P, 2 equals D, 3 equals F. Okay, and these are the type of orbitals that you're always going to get. All right, your L, you're only going to get these 4 different values. That's it for your quantum number here. So the next quantum number is our magnetic quantum number. So basically, how you guys want to think about this, this definition tells you the orientation of your orbital. All you guys need to understand with this orbital is that it's going to tell you, right, in this case, how many orbitals are in that sub level. Okay, so for instance, let's go back to if our L is 2. So this example. So say we got our principal quantum number is 3. Our angular momentum number is 2. So, right, if our L is 2, that means that for our L is 2, so that means our D, right, our D orbitals, that means that it's going to have, in this case, 5 orbitals. So essentially, if our L is 2, right, we're doing this here, minus L to positive L. So in this case, it's going to be minus 2, minus 1, 0, plus 1, plus 2. So that's 5 different numbers. Well, that's 5 orbitals. That's all that means. So for example, if I had, P, well, that would be, what's P? 1, so negative 1, 0 to positive 1. So that's going to tell me if I got an L value of 1, I got 3 orbitals. And it's always going to be the same, right? So once you know this, you kind of know this forever, okay? Because it's not going to change. It's not going to change. The last thing we're going to talk about is our spin quantum number. This is basically going to tell us how our electrons are spinning because we understand, right, that our electrons are negative and are always spinning. All right, and because they're always spinning, this is where we're getting that magnetic field from. So there's only 2 directions for this. You either spinning up or you spinning down. That's it. And we use these values here, plus half and minus half, for those spinning electrons. So basically, you got your principal quantum number, your angular momentum quantum number, and your magnetized quantum number, right? That's going to describe an orbital for you, okay? Now, your orbitals with the same value of your n, so your principal quantum number, that means that they have the same energy. The orbitals that have the same principal quantum number and the same angular momentum number are going to be in the same sublevel, okay? And the number of sublevels in any level will be equal to n, so that's going to be your principal quantum number. Now, here's a little other thing that you can use 2L plus 1. This is basically what we calculated for our angular momentum number, but it's just kind of the quicker way. It's not really quicker. Once you know this, you kind of know this. But basically, this is summed up here, right? Your S sublevel, this is when your L is equal to 0, you're going to have 1 orbital, right? P, if your L is equal to 1, you're going to have 3. So once again, everybody, this is when we were doing the plus 1, 0, negative 1 thing, right? This means we got 3. D cell level, we're going to have 5. F cell level, we're going to have 7. Okay, that's basically it. It's always going to be the same, right? P is always going to have 3 orbitals. S is always going to have 1. D's always got 5. F's always going to have 7. That's not changing, okay? So when we go and just look at this here, this is what we want to understand. My principal quantum number N, this is my lowest energy, right? my lowest energy. Because it's the lowest energy, that means that we only got one orbital, one s orbital, okay? And it got our orbital right here. My principal quantum number is equal to 2. That means that, okay, I can have multiple orbitals in this case, right? Because we increased our energy. So I can have a 2s orbital and a 2p orbital. And if I go up to my n is equal to 3, now that's more significant, right? We got larger amounts of energy. So we can have a 3s orbital, a 3p orbital, and a 3d orbital all in that same energy level, okay? And in this case, this is where we see those orbitals. S orbital has, our S sublevel has one orbital, 3p sublevel will have three orbitals, and our D orbital, in this case, has those five there.